In this video, we will be looking at whether the converse of the divergence test is true or false, and in doing so, we will look at another important series known as a harmonic series. So let's first recall what the divergence test says. If the sequence of ANs does not converge to zero, then the series of ANs diverges according to the divergence test. We want to know if the converse is true. And what is meant by converse is, in other words, is it true that if the series of ANs diverges, then the sequence of ANs does not converge to zero? So in order for us to answer this, we're going to look at a very important new series that not only will help us answer this, but will be used with some of our series tests in the future. And that series is called the harmonic series. The series of 1 over k's as k goes from 1 up to infinity is called the harmonic series. And the reason it's called that is because it's connected to the harmonics of vibrating strings, such as those on a guitar. What we're going to do here is study whether this series converges or diverges, and we're going to take a special approach to this specific one to see if it converges or diverges. We're not going to look at all the partial sums. We're going to specifically look at the partial sums of this particular form. 2 to the n, of course, represents the powers of 2. So we're going to look at s sub 2, s sub 4, s sub 8, s sub 16. Again, 2, 4, 8, and 16 are all powers of 2. And then we're going to see if we can generalize a pattern from there. Of course, recall that s sub 2 is a sub 1 plus a sub 2. And in this case, that would be 1 over 1 plus 1 over 2, which of course is 3 halves. We'll write this as the decimal 1.5. Now, somebody who has done this in the past has realized a pattern here. So what we need to do is compare our result, in this case specifically to the number 2 over 2. Well, of course, 2 over 2 is 1, so our 1.5, or our second partial sum, is greater than 2 over 2. Let's now take a look at s sub 4, which of course is the sum of the first 4 terms of the series. So s sub 4 is equal to 1 over 1, which is 1, plus 1 over 2, plus 1 over 3, plus 1 over 4. To save time, I've already done these computations with Desmos, and instead of putting it in fraction form, we're simply going to round this to the thousandths place. So this is approximately equal to 2.083. And with s sub 4, we want to compare that to the number 3 halves, which is equal to 1.5. So our number 2.083 is greater than 3 halves. Now, if we look at s sub 8, which is the sum of the first 8 terms, I'm not going to write out that sum like this, simply going to give you the decimal approximation. S sub 8 is approximately equal to 2.718. And let's put in s sub 16 as of now, and that's approximately equal to 3.381. Now for s sub 8, we're going to compare that to 4 halves, which of course 4 halves is 2, so 2.718 is greater than 4 halves. And we're going to compare s sub 16 to 5 halves, which is 2.5. And of course, s sub 16, which is 3.381 approximately, is greater than the 5 halves. So while this does not constitute proof in any way, we want to see a pattern here. As we go up by 1 in the power of 2's, notice that each time this number is growing by a half. So you might be able to surmise that s sub 32, which is the next power of 2, is greater than 6 halves. And you might guess that s sub 64 would be greater than 7 halves. Again, this is not a formal proof, but it actually is true. Now, since there are infinitely many powers of 2, there's always going to be adding on another 0.5. And if you were to do that infinitely many times, this sum would diverge. So while this, again, is not a formal proof, we now should be fairly convinced that the harmonic series diverges. Now that we've given an informal argument that the harmonic series diverges, we can return to our question of whether the converse of the divergence test is true or not. So again, that converse is the statement, if the series of ANs diverges, then the sequence of ANs does not converge to zero. And now, because of the harmonic series, we can see that this is false. The harmonic series, again, was as n goes from 1 to infinity of 1 over n. We saw roughly informally that this series diverges. But notice that if we look at the sequence of ANs, just the sequence of 1 over n's, that sequence converges to specifically to 0, because the limit of 1 over n as n approaches infinity is equal to 0. So we have a divergent series, yet the sequence associated with it actually converges to 0. So this in general is not true, the converse of the divergence test. So in other words here, in summary, fill in the blanks below. If the sequence of ANs converges to 0, then the series may or may not converge. It may or may not converge. We cannot say based on whether the sequence of ANs converges to 0. We will have to try something else. However, if the sequence of ANs does not converge to 0, then we can conclude that the series diverges because of the divergence test.